quite interested in biology and astrophysics. But today, I've stuck on to my most favorite, astrophysics, especially about the universe and its origins.
The sun is the source of most of our energy here on Earth. Energy from the sun is used to produce electricity using photovoltaics and solar thermal plants. That same energy is also used for heating using solar domestic hot water systems, hydronic heating, solar air heating, and solar cooking, just to name a few. This video will talk about how the sun produces that energy. The sun produces energy using a process called fusion. Let's start our explanation of fusion with the atom. You've no doubt heard that everything is made up of tiny things called atoms. We use a very simple physics model to describe them. At the center of an atom are protons and neutrons. We call this center the nucleus of the atom. That's where the word nuclear comes from, since anything to do with nuclear deals with stuff in the nucleus of the atom. And to complete our model, circling around the nucleus are electrons. Different types of atoms have different numbers of these parts. This is one variation of a hydrogen atom, just a single proton and an electron. This is another variation of a hydrogen atom. It has a neutron added to the nucleus. This variation is called deuterium. And just to show you a more complex one, this is a carbon atom. So back to the sun and the process of fusion. For this we'll ignore the electrons, since we're dealing with the nucleus of the atom only. The sun also is made up of atoms. Since the sun is so massive, it has extremely strong gravity, much stronger than the gravity here on Earth. This gravity pulls the atoms together. Normally the nuclei of the atoms don't want to get close together. The protons repel each other. But the sun's gravity is strong enough to overcome that, and when two atoms get close enough together, they merge, or fuse, to become a new atom. And that's where the term fusion comes from. So how does this produce energy? Well, take the example of our deuterium atom with its proton and neutron in the nucleus. Again, we're ignoring any electrons. It takes energy to hold neutrons and protons together in a nucleus like this. Let's make up a pretend amount for the quantity of that energy, 3. The actual amount isn't important for understanding the concept. We'll bring back our hydrogen atom. Since it has only a lone proton in its nucleus, there's no energy needed to hold things together. There's only the one thing. So the total amount of energy holding stuff together for these two atoms is 3. When the sun fuses these two atoms together, a new type of atom is produced, called helium. As you can see, it has 2 protons and 1 neutron in its nucleus. The energy needed to keep this atom together, though, is only 2. But remember, we started out with an amount of energy 3, and now we're using only 2. So where did the extra energy go? In this case, it's sped away with this expanding wave called a photon. A photon is an electromagnetic wave that has energy and expands outward as a large sphere-shaped wave, carrying away our missing energy of quantity 1. So the total energy is still 3, 2 to hold the new helium atom together, and 1 carried away elsewhere by the photon. But only a small portion of that wave and energy will hit our solar panel on Earth, so we'll illustrate that small portion as this fuzzy wave particle thing.
This is the dying star, VY Canis Majoris. It's more than 1 billion miles across. Like all stars, it's a giant nuclear fusion reactor, pumping energy outward. At the same time, the star's extreme gravity crushes inward. For a few million years, fusion and gravity are locked in standoff. But when the star runs out of fuel, fusion stops, and the stalemate ends. Gravity wins. In a millisecond, the core shrinks to a fraction of its original size, and a baby black hole is born. Immediately, it starts to cannibalize what's left of the star. The new black hole in the middle keeps feeding on the body of the star around it. It eats the gas so fast, it chokes and coughs. blasting out huge beams of energy.
They basically eat their way out from the star. Basically, the star is dead before it hits the ground.
Finally, the star explodes. In 1 second, it blasts out 100 times more energy than our sun will produce over its entire life. What's left is a new black hole and 2 jets of energy hurtling through the universe at the speed of light. These jets are called gamma ray bursts. Most of them last only a few seconds, and they fry anything in their way.
You would have seen what happens inside a star, the example of the nearest star, the sun, and also about what happens after all the fuel of a star burns out. That is, could form a black hole, nebula, or a gamma radiation. Well, this could not happen with our sun because it's a really small star. This could only happen with huge stars like red giants or blue giants. Okay, how did the universe form? Well, you'll have an idea. The Big Bang Theory. I believe in this theory. Also, I believe in the inflationary model proposed by Guth, which tells us that the universe started expanding at once after the Big Bang. Black holes are also formed by a similar action to the Big Bang. Black holes in our universe have no dimensions at all. Inside black holes, there is no point, and space-time is also absent. And our universe has 4 dimensions: length, height, breadth, time. Actually, space has 10 or 11 dimensions, but we don't consider it now. I told you that our universe has 4 dimensions. Let's take an example of a cup on a table. We know how a cup is, and in our universe, it exists in the form as the 4 dimensional cup. When we push the cup down, it breaks into pieces. You cannot join it back, and this is the 4 dimension time. Time passes, but you can never bring back time. But in black hole, there is nothing called this. Even we don't know whether a cup exists inside a black hole or not. What if the universe itself is a supermassive black hole in some other more dimensional super universe? Well, this could prove the emergence of new stars. It will also prove dark energy and dark matter. Well, that's all for me to say. Bye bye.